Hey guys, today we're going to talk about section 4, power and intensity, and also talk about the decibel scale. So we're still talking about waves, and we'll start by talking about harmonic waves on a string. So um, the idea is that for any point on the string, all the power that's in the length of the string is going to pass through that point, or I guess I should say all the power in the length of the string that's equal to a wavelength. So if there's multiple wavelengths taking place on one string, it'll just be the power of that one wavelength. But it's interesting because all that power is going to move through that point even though the string isn't actually moving. So just remember that the basic formula for power is E energy over T, the period. I'm sparing you a lot of the substitution and stuff, but this on the second line there where it says P equals 2 pi squared mu V F squared A squared, all of that is actually going back to the simple harmonic motion from chapter 15 and doing some substitutions with that. So, if you want to go back and look up some of those formulas, you're welcome to, but the derivation for that formula I don't feel like is worth the time that it would take to get it done. So just note all of these different symbols here, the mu being the mass density, the wave speed, frequency, etc., etc. So for example number 7, we have a 10 hertz harmonic wave of amplitude 5 centimeters traveling at 30 meters per second along a string, having a mass density of 0.02 kilograms per meter, and we'll find the power transmitted moving over to the document camera. All right, so with example number 7, this is actually a fairly simple example. The formula is not simple, but the working of the problem is pretty simple. Our formula here for power is on a previous slide on the notes, 2 pi squared mu V F squared A squared, where we have mu is the mass density, V is the wave speed, F is the frequency, and A is the amplitude. So we have all of these pieces provided for us. So 2 pi squared mu is 0.020 kilograms per meter. V is the wave speed, that's 30 meters per second. F is 10 hertz, so 10 hertz, 10 hertz squared. And then A, our amplitude, is 5 centimeters. We want to do that in meters, so 0.050 meters, and that is also squared. So we just need a calculator to plug all this in, and it looks like we've got two significant figures from both this one and this one. Actually, this one would be 1 technically, wouldn't it? What is originally given as, it's given as 10 hertz. So technically this is 1, but I think the textbook in this example uses 3.0 watts as the final answer. So you could argue that this should really be one significant figure, but to keep it consistent with what you would find if you went and looked in the textbook, I'll provide the answer here as 3.0 watts. All right, here's example number 7. All right, so in contrast to waves that are on a string, so think when I say waves on a string, think of like guitar strings or piano strings, things like that. But unlike motion on a string where the wave just stays on the string, now granted it does transmit sound to the air around it, but the wave is just staying on that string. When we talk about sound waves, we're talking about waves that are propagating out in all directions. So we have a little tricky situation here with this because we have to introduce a new idea called the cross-sectional area, which your book uses a much fancier A than what I could find for these notes, but that sort of stylized A, that's our cross-sectional area, as opposed to the regular block A that is the amplitude of the wave. So if we have that power formula from last time, the only thing that really changes is that now we have rho, which is that symbol that looks like a P, rho times the cross-sectional area, so the density times the cross-section. So most of the time the cross-section that we're going to be considering is a sphere. the sound waves propagate out in all directions, and so the surface area of that sphere will be our funky A, that stylized A. All right, so you guys have probably heard of the decibel scale. You may not know exactly how it works, but you know that things that have a higher decibel value are loud, and things that have a lower decibel value are quieter. And so this kind of just should give you a better picture of how that works exactly. Typically, the lowest sound that anybody can hear is 1.0 times 10 to the negative 12th watts per square meter. That's the intensity level. I is going to represent intensity for us. So the frequency that happens at, I think, is typically around 4,000 hertz. So it's a pretty high-pitched sound. You can hear a high-pitched sound at a much lower frequency than you can a low frequency sound. So 10 to the negative 12th is about the lowest, and then 10 to the 12th is where sounds, 10 to the 12th times I naught. That's where sound starts to become painful. So loud rock concerts, aircraft taking off, like jet planes taking off, things like that make really loud noises. Those can actually be painful and can cause damage to your ears. So the decibel scale itself is actually a logarithmic scale. So this beta that you see, beta equals 10 log of I divided by I naught. So it's, we tend to think of scales in linear terms, that the difference between, say, let's kind of use some easy numbers maybe. The difference between 100 and 110 decibels is not the same as the difference between 110 and 120. Even though it's a 10 decibel difference, it's not 10. It's not the exact same difference in terms of actual loudness. Okay, it's because it's logarithmic. A change of 1 in the decimal scale is actually a change of like 10 times as much intensity. So for the decibel scale to go up by 1 multiplies the loudness by 10. So the differences increase as you get higher in the scale. Okay, so maybe an easier way to think of it is like going from 80 to 81 is a pretty small difference. Going from 100 to 101 is actually a pretty big difference. That may be a little more illustrative. All right, so we have a couple examples, well, an A and a B example to work here. Start with a person 2 meters away talking in a normal voice that's 60 decibels. And we want to know how much power is being delivered by the person talking. So we'll assume that the sound propagates in all directions in a sphere, and we'll work it like that. And then in part B, we'll see what's the intensity level at 6 meters. So we know that when we're up close to somebody, we can hear them whispering much easier than if we're far away. So we'll do some calculations that pertain to this to give us an idea of how that works. All right, for example number 8, we have a person speaking to us from 2 meters away at 60.0 decibel intensity level. And that actually is something that we probably ought to point out and make sure that we're clear on. We have two different terms. We have intensity, okay, and those I values that you saw in the notes, or that you're seeing in the notes, those are intensity. But then intensity level is that decibel value, okay? So the intensity is measured in watts per meter squared. The decibel is kind of how loud we perceive that, and it's got its own scale, the decibel scale. All right, so to calculate part A, we want to know what's the power with which this person is talking. So I can use red, that'll be okay. B equals, or beta equals, 10 log I over I naught. All right, so power overall is going to be our intensity times the surface area. So we've got to work our way into finding the intensity right here. Okay, we've got to find this I. So if we put our 60.0 decibels in there, equals 10 log of I over I naught. Then I'm going to divide both sides by 10. So this will be 6.00 equals, I'm going to drop the units for now if you don't mind too much. I know it's a little bit lazy of me, but then we have that. So now if I want to get rid of that log, remember that's a log base 10. So from pre-calculus or from algebra, wherever you may have learned this, when we want to solve a logarithm, we can do that by rewriting it as an exponential. So this becomes 10 to the 6th, or 10 to the 6.00 technically, equals I over I naught. So finally, when I want to get that intensity level I all by itself, I will equal I naught times 10 to the 6th. Okay, so what is I naught? Well, from the notes, we said that I naught was basically the quietest sound that the human ear can typically perceive, and it's equal to 1.00 times 10 to the negative 12th watts per square meter times our 10 to the 6th value. That will be our intensity, which the math on this isn't too bad. 10 to the, that should be a 12, sorry. 10 to the negative 12 times 10 to the 6 is going to be 10 to the negative 6th. Technically 1.00, so we get the right number of significant figures. That's our intensity. So now we're wanting to figure out the power. Okay, so we have intensity. To figure out power, remember that power is going to be equal to intensity times the surface area. So if we're assuming that this person is speaking and that the sound propagates in all directions equally, then that we're talking about a sphere. Okay, so the surface area for a sphere, and I'm trying to make this A look a little bit stylized so that you don't confuse it with amplitude. This A will be the surface area A. Is 2.00 meters because we're 2 meters away from this person. So sorry, that's not what I want. I wanted to write the formula. A is, let me just start that line over. Sorry about that. A is 4 pi r squared for the surface area of a sphere. So our R is 2.00 meters. So this is going to be 4 pi times 2.00 meters squared, which is 16 pi square meters. All right, so finally, last line here, we want to find the power. So we're going to multiply our intensity, which is 1.0 times 10 to the negative 6 watts per meter squared, times our surface area, 16 pi meters squared. Sorry, I did that kind of funny. That's okay, actually. Sorry, now it's just ugly. But it says 16 pi meters squared. So when we multiply this together, we get, what do we get? 5.03 times 10 to the negative 5th watts. Okay, so that's the power with which this person is speaking. All right, so for part B of example number 8, we want to know the same person is talking, but now we're at a distance of 6 meters. What is the intensity level? So at 6 meters, here's the thing to realize. At 6 meters, let me choose a different color here just for a second, a little aside. Okay, before we were at 2 meters. Okay, now we're at 6 meters. So this is triple the distance, right? Well, the surface area increases with the square of the radius. So the surface area for this sphere of sound as it goes away from the speaker, the surface area is actually 9 times greater. Okay, so the radius has tripled, the surface area has increased by a factor of 9. So if we want to calculate our new, let me go back to purple. If we want to calculate our new intensity, okay, I prime is going to equal that original intensity at 2 meters divided by 9. Okay, we've we've increased the surface area by a factor of 9, so we need to divide by 9. So this would be 1.00 times 10 to the negative 6 watts per meter squared. That was the value that we found in part A for the intensity. And we divide that by 9. And we get 1.11 times 10 to the negative 7th watts per meter squared. Okay, so the intensity has decreased a good bit. So now what we want to do is use that in our intensity level formula. So beta equals 10 log of I over I naught. So beta is what we're trying to find this time. That's the intensity level. So I just need to plug in my pieces. 10 log of 1.11 times 10 to the negative 7th watts per meter squared over 1.00. This is the I naught from before, 1.00 times 10 to the negative 12th watts per meter squared. And then we do that calculation in our calculator. You should get 50.5 decibels. All right, so that concludes example number 8. For example 9, similar kind of situation, only we're going to see how frequency affects intensity level. All right, for example number 9, we're actually looking for the amplitude of some sound waves as they travel through the air. So in part A, we're looking at a 1000 hertz frequency, and we want to look at it at 2 different intensity levels, 0 decibels and 160 decibels. And then in part B, we'll look at the same calculations, but with a 100 hertz signal instead of 1000. All right, so to begin with here, our formula for intensity is going to be 2 pi squared rho v f squared a squared. So if we solve this equation for A, because we're looking for the amplitude this time, we get the square root of I over 2 pi squared rho v f squared. Okay, so notice that I'm saying rho instead of p. That's technically a rho. It's a Greek letter rho. It's the mass, sorry, the density of the air. All right, so with a 0 decibel intensity level, that means that our intensity, I, is actually I naught, which is 1.00 times 10 to the negative 12 watts per meter squared. So our density, and this is actually the density, a couple of these values come from tables in the textbook that you may or may not have noticed as we were going through it, but the density of air at sea level at 20 degrees Celsius is 1.20 kilograms per meter squared on average. And then our speed of the wave through air is going to be 344 meters per second. That's a calculation that we found together in a previous lesson. So now I think we have everything that we need. We've got I, rho, v. We know the frequency is 1000, so we can find the amplitude here. So this is going to be big square root 1.00 times 10 to the negative 12th over 2 pi squared, 1.20 kilograms per meter squared, and then 344 meters per second, and then 1.00 times 10 to the third hertz. Okay, so 1000 hertz. We'll do it as 1.00 times 10 to the third hertz. I think missed a unit here. This should be watts per meter squared. All right, so I think that's everything. Now we just go to the calculator, and we should be able to find that this is 1.11 times 10 to the negative 11th meters. So, interesting little note here in the textbook. 1.11 times 10 to the negative 11th meters is actually smaller than the width of the smallest atom, which I assume would be a hydrogen atom. And yet, the human ear is capable of hearing a sound that moves air that little, which is pretty fascinating. All right, so the next part of this is to find at 160 decibels, what would be the amplitude in that case? So we don't have to go all the way back to the very beginning to calculate this, because we can make an observation that as I increases, A is going to increase according to the square root of I, since I is inside the square root. So at 160 decibels, we're looking at 10 to the 16th times as intense a sound as 0. So this is going to be 10 to the 16th times I naught, okay, which is what we used up there. So our new amplitude, therefore, is going to increase by the square root of that. So it's going to be square root of 10 to the 16th times our original I naught. I'm sorry, times our original A, And then that's going to give us this, what is that, 10 to the 8th, right? We don't need to keep the square root around. Square root of 10 to the 16th is 10 to the 8th times our original value, 1.11 times 10 to the negative 11th. So our new amplitude at 160 decibels is 1.11 times 10 to the negative 3rd meters. So what is that, about a millimeter? So we've gone from smaller than the smallest atom to about a millimeter. All right, so that concludes part A of example number 9. Okay, for part B of example number 9, we want to find the same values but with 100 hertz instead of 1,000 hertz. So there's something really important to remember here. When we're talking about these calculations, instead of having to go back to the beginning every time, if we can come up with a relationship that will help us simplify things, then that will be very helpful. So to go from 1,000 hertz down to 100 hertz, we've cut the frequency, we've basically divided it by 10, right? Well, remember that the amplitude here, if we notice the formula, the amplitude is proportional to 1 over the frequency, right? The frequency was in the bottom of that square root. And actually, let me bring this over. See, there it is, f squared. Okay, so the square root and the squared essentially cancel each other out when we think about the proportionality in this case. So I shouldn't say it equals 1 over f, but it's proportional with 1 over f. So if I have decreased my frequency by a factor of 10, then I'm going to increase my amplitude by a factor of 10. So the new amplitude for this is just going to be 10 times what it was for the first part of example 9a, which our answer to that part was 1.11 times 10 to the negative 11th. So 1.11 times 10 to the negative 10th. Okay, so still pretty darn small. Then for 100 hertz, or 160 decibels, sorry, the same calculation, but using the second number. So we're 10 times as much as our second answer to part A, which was 1.11 times 10 to the negative 3rd. Okay, so multiplying that, we get 1.11 times 10 to the negative 2nd meters, which is actually 1.11 centimeters. All right, so we're going to skip 16.5. It is basically a lot of graphing trig functions is basically what this section boils down to. So for now, that'll be the end of this lesson. We'll pick up with 16.6 in the next video.